Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In this video, we will use a Python program that uses the Fortran MKL library on the Betzy Linux cluster. After logging into Betzy, we access the Login 3 node. For our production jobs using MKL with Python, we'll be using the work folder. I've created a folder named MKL Python within the work directory. Inside the MKL Python folder, we have 3 files with the same name but different extensions. First, let's examine the file with the F90 extension. This file includes the initial Fortran subroutine we discussed in video 36. Following the initial subroutine, there is another subroutine named MKL, DGEMM. In this subroutine, matrices A and B are inputs, and matrix C is the output. It utilizes the MKL routine DGEMM, which we explained in video 31. Then we'll look at the Python file. We will use a matrix dimension of 32,768 and utilize both Fortran modules. Therefore, we'll apply the Fortran MKL routine for matrix multiplication instead of the NumPy routine used in our last video. Let's examine the JavaScript file with the sh extension. This script is the same as we used in our last video, and it requests 128 cores on a single node. We'll load the matplotlib module, which also loads NumPy and the Fortran, to Python command. We're setting OpenMP environment variables. The Fortran module is built using the same Fortran to Python command demonstrated in our last video, but now we have included the option for loading the Fortran MKL routines. We'll execute the Python program and use script commands to measure the build and execution time. The remainder of the job script is unchanged from our last video. Before submitting the job to the Slurm management system, we clear the terminal. Once submitted, the job is assigned a job ID number. Using the SQ command with the me option shows that the job has been computing for 18 seconds. After the job completes, we examine the Slurm output file with the correct job ID number. The matrix multiplication was completed in approximately 82 seconds, using the Fortran MKL routine with Python. In our last video, the NumPy routine completed the same job in about 35 seconds the first time and 37 seconds the second time. This demonstrates that the NumPy routine offers better performance than the Fortran MKL routine with Python on Betzy. Therefore, it's advisable to first check if your calculation can be performed with a NumPy routine before considering a Fortran MKL routine. However, both NumPy and Fortran MKL routines generally provide better performance than what you might achieve independently. It's always beneficial to investigate whether your calculation can be handled by routines from NumPy, Fortran MKL, or other known high-performance libraries. Let's examine the files created in the folder. we notice new files, including copies of the original files used in this computation, with the job ID number appended to their file names. The file with the long name, highlighted in green, contains executable Fortran modules that the Python program can utilize. This file is generated by the Fortran to Python command. Let's examine the output file generated by the Fortran to Python command. It indicates that 2 Fortran subroutines will be converted into Python modules. The file also provides guidance on how these modules should be used in the Python program. In our Python program, we followed these instructions, with the addition of the prefix fort before using the module names. Before submitting the job once more to obtain a better measurement of CPU efficiency, we will clear the terminal. First, we'll make some changes to the job script with the Emacs editor. We'll skip the building process of the Fortran module, as it is already built. This approach will provide a clearer indication of CPU efficiency during parallel computing. After submission to the Slurm management system, the job is assigned a job ID number. We see the job has been active for 21 seconds with the SQ command. We can examine the Slurm output file for this job using the correct job ID number. The matrix multiplication was now completed in approximately 86 seconds. The CPU efficiency was now around 86%. To use the scripts and files from these videos as templates for your work, you may copy them from the Saga Linux cluster. First, move to the folder, Cluster, Work, Support, Parallel, Computing, YouTube. Use the ls command to display its contents. You'll recognize many scripts and files from the videos, and you can copy any of these files to your home folder. In our next video, we'll explore the new Olivia Linux cluster. I am looking forward to the next video, wishing you all happy computing in the meantime.